So after having looked at the classification of substances, then looked at the type of mixtures that we have, we now go further to look at the method of separation of mixtures. So we have looked at the mixtures that we have. We have solid, liquid mixtures. We have miscible and immiscible. Liquid mixtures. We have miscible and immiscible. Solid, liquid mixtures. Solid, liquid mixture. We have soluble and insoluble. Then we have solid mixtures. Solid mixtures, that those ones that are they are melted to form alloys. So we are looking at the methods of separating mixtures. So we say that mixtures can be separated from applying the following methods. Remember, mixtures are separated depending on the physical. They are separated using physical means. So they are separated using the physical means, and the methods are as follows. The first one, we have decantation. The first one, we have decantation. So decantation. So sediments can be separated from a liquid by pouring out the liquid. This process is called decantation. So decantation is a kind of a separation process that is used in separating solid liquid mixture that they are insoluble. They are insoluble. So the solid is insoluble in the liquid, so we can use decantation, where we decant the solvent and we remain with the solute. And remember, this type of method is not that efficient, because some of the solvent will remain in the solute that will obtain that we will obtain. Now let's look at the experiment that we want to carry out. So we put sand in a beaker, add about 200 centimeter cubic of water, allow it to settle. Then we pour off water carefully into another beaker. After having done that, so after having put some sand in a beaker, then we added water. Remember, now we have a mixture. We have a mixture of water and sand, but not a solution. So observation: sand settles at the bottom as the sediments. So less clean water is poured out. Remember, this water has some particles. The light particles that are found in the sand, they are able to be poured out when decanting. They are able to be poured out when decanting. So let's explain this instance. So sand does not dissolve in water. Sand is denser than water and thus settles at the bottom as the sediment. So when poured out, the less dense water flows out. And remember, we will not obtain the entire of the liquid that we had at the beginning, because some of the water will remain. So this method is not that efficient. So another method is filtration. And remember, we use each and every method depending on the characteristics of the substances that are being mixed. Now let's look at filtration. So decantation leaves suspended particles in the liquid after separation. So filtration thus is an improved decantation. So remember, we said that decantation is not that efficient. So now there is an improvement on the decantation. So we have filtration. So filtration is the method of separating insoluble mixtures or particles or solids from a liquid. So let's look at this experiment. to separate soil and water using filtration. So fold a filter paper to fill well into a filter funnel. So remember, filter paper is circular. It's a circular. So we first fold it into half. We first fold it into half. Then again, this half we fold it now into, so the half of the half is a quarter now. We first fold into half, then fold it into quarter. So at that we will obtain our filter paper. Then after having folded it, we now open one of the one of the pieces that we have. We now open one of the pieces that we have, and then we place it in a filter funnel. We place it in a filter funnel. We fit it in a filter funnel. So we place the filter funnel in an empty 250 cubic centimeter beaker. After having now placed there the filter paper in the filter funnel, now we start pouring out. We start pouring. They now start pouring. Start pouring the mixture that we have. The mixture that we have. So remember now in this we put one spatula handful of soil into 50 centimeter cubic of water. We put the soil or the soil into the filter funnel. So at the beginning we had water that is pure, and then we had soil that is pure. So we mix them. After now mixing them, we have now a mixture of water and soil. So after having folded our filter paper, placed it in the filter funnel, now we pour the mixture in the funnel fitted with the filter paper, and now we let it now filter out the liquid. So what's being filtered out is called filtrate. Now the liquid or the solvent that now is being filtered out through the filter paper using the funnel is called the filtrate. And now what is remaining on the filter paper, what remains on the filter paper, now the soil that is remaining on the filter paper, we have soil that remain on the filter paper. We have the soil that remain on the filter paper. So we have clean water is collected before the filter funnel. Soil remains above the filter paper. So we say that the water, so because the filter paper is porous, it allows the water to go through, which we are calling as the filtrate. So a filter paper acts as a sieve that has some invisible holes in it. So the holes allow smaller water particles to pass through, but not allow bigger soil particles. So the liquid which passes, we are calling it filtrate, and the solid you do not pass we are calling it residue. So we have the residue that is remaining now on the filter paper, and now the filtrate now that has passed through the filter funnel. So remember now we are obtaining now water with no other particles, because it has now been filtered through the filter paper, and now we obtain also the soil as the residue on the filter paper. So now this is the setup. This is the setup of the apparatus. We have the filter funnel. We have the filter paper inside the filter funnel. we have now the residue on the filter paper, which is the sand remain. Then we have now the filtrate, which is now water inside the beaker or the flask that we had used. So in industries, filtration is used in engine filters to keep to clean up the air. So in industries we have filtration that is being used. Now it does not only just it's not a matter of just learning it here, but it also applies more and more. So you have this concept being used in engines, where there is filters to clean up the air. We have filters to clean up the air. We have filters to clean up the air. So then you have now purification, process of purification of water or treatment of water. So it is not only in engine, but we also use it in purification of water or treatment of water. So in the first, we have the main source of water. If you can see this diagram here, we have now here the main source of water. So this now intake. This water is either from rivers, from lakes. So then this now the source. From the source, we pump this water into sedimentation tank. So we have heavy solid, and now in this tank, the heavy solid will settle. The light or the floating materials are now skimmed off in the sedimentation tank. Now remember, this is a process where we are now cleaning the water from either the lake or the river for now the consumption and so many more other functions. So from now the sedimentation tank, we are now pumping this water in the filtration tank. We are pumping this water into filtration tank. And remember, in the filtration tank, we have stones or the sand. Now the coarse sand at the bottom, then we have fine sand at the top of it, and now we are adding in water. So after having pumped this water from the sedimentation tank, we are now bringing this water into the filtration tank that has some fine sand and then coarse sand. So the fine sand at the top helps so that in case of any materials that are from the sedimentation tank have come up with this water, they are now being able to be trapped. Because now at the bottom we have coarse sand or the stones. They not allow these materials now to pass. Those materials will be trapped there and they remain there. Then this water is now being pumped to the chlorination tank. So chlorination tank, we add chlorine into the water. The water is chlorinated using chlorine. Then from the chlorination tank, now this water is now clean and ready for consumption or for any other use. Now it is pumped to the clean into the storage tank or the reservoir. Then now there we have an outlet to collect the water. Then now there you have an outlet to collect the water. So that's how water from the lake or the river is now cleaned and made available for consumption. Now let's look at another method. Remember, we started with decantation, looked at filtration. Now we are looking at another method of separation, which is evaporation. So evaporation is a method of separating a solid. Remember, we said a solid is a solid from its solution. Now, from the solution now, this involves heating a solution. Remember, we said that solution is formed after we have a solute that has completely dissolved in a solvent. So we are heating a solution, which is a solvent, and a solid to vaporize the solvent out of the solution mixture, leaving pure solute or the solute. So in the mixture, if a mixture contains a soluble solid, they are just filtered out. So in case of the suspension of the precipitate, so if they are insoluble, for the insoluble solid liquid mixture, we just use filtration. But for the soluble ones, now we are using evaporation. Now let's look at an experiment on how we can separate a mixture of soil and salt. Remember, now salt is sodium chloride. So for example, you have accidentally mixed soil and salt. What do? We will not leave it. When we leave it, it will be a waste of resources. Remember, now sodium chloride has some uses. So we have a procedure here. So we put one spatula end full of soil on a filter paper. We put one spatula full of common salt or sodium chloride into the same filter paper. We mix well using the spatula. Then now, after having mixed them, remember, each one of them has retained the physical characteristic and the chemical. But now we add, for us to separate them, we have to add water. When we add water, you'll find that the salt will dissolve. Then we remain with the sand settling at the bottom, or the soil settling at the bottom. Then some suspensions at the top of it. After having mixed well in water, we put the content of the filter paper into the water. We steer now thoroughly. We said steering helps it now to dissolve faster. Then we fold a filter paper into a filter funnel. We pour a half portion of the content of the beaker into the filter funnel. So we put the filtrate in an evaporating dish, heat on water bath. So after doing all that, the following is what we will observe. Now, on mixing, colorless crystals and brown soil particles appear on the filter paper. Now, on adding water, common soil dissolves in water. But soil particles do not dissolve in the water. Common salt dissolves in water. Soil particles do not dissolve in water. Soil particles do not dissolve in water. Then on filtration, colorless liquid collected as filtrate below the filter paper or the filter funnel. So you have a colorless liquid collected as filtrate, brown residue collected above the filter paper or funnel. Now the colorless liquid is now a salt solution. The brown residue is now the water. It's now the soil. The soil. Then on evaporation, now we are now heating now the solution, the salt solution, the filter that we had obtained. The filter that we obtained. Colorless crystals collected after evaporation. The colorless crystals are collected. Now remember, on evaporation, as we are heating now, the water is evaporating, leaving the crystals of the common salt. So solid mixture of sand and common salt take the color of the two. So solid mixture of the sand and common salt take the colors of the two. So on adding water, common salt dissolves to form a solution. Soil does not dissolve because it is insoluble in water and thus forms a suspension. So on filtration, a residue of insoluble soil does not pass through the filtrate, does not pass through the filter paper. Now it is collected as a residue. Then common salt solution is collected as filtrate. Now on heating the filtrate, the solvent or the water vaporize out of the evaporating dish, leaving common salt crystals. Common salt crystals. So vaporization or evaporation can take place even without heating. This is principal process of drying wet clothes on the hanging line. Remember, now we wash our clothes. We wash our clothes with water and we hang them. We do not provide any heat. They are dry using the sun. So you can see the apparatus set up. So we have a source of heat, we have the tripod stand, we have the water bath, we have the beaker, we have the wire measure, the wire gauge, we have the common salt solution, then the evaporating dish. So another method of separation, we have distillation. So distillation is an improved evaporation. So remember, you said filtration is an improved decantation. Then now distillation is an improved evaporation, where both the solute and the solvent in the solution are separated and collected. Remember, now in the evaporation, we did collect water or the solvent that we are using, but in the case of distillation, now is a now improved one, where we collect each and every of the substances that were mixed. So distillation, therefore, is the process of separating a solution into constituent, solid, solute, and the solvent. It involves heating the solution to evaporate or vaporize the solvent out. The solvent vapor is then condensed back to a liquid. Now let's carry out an experiment to see how we can actualize this method. So to obtain copper 2 sulfate crystals, to obtain copper 2 sulfate crystals and water from copper 2 sulfate solution, Copper 2 sulfate solution. Now the procedure: we put a spatula handful of copper 2 sulfate crystals into a 250 cubic centimeter beaker. Then we place about 200 of water, 200 cubic centimeter of water into the same beaker. Then we stir thoroughly using a glass or stirring rod for about 1 minute. We put half portion of the content in the beaker into a round bottom flask, bottomed or flat or conical flask with broken porcelain or sand or glass in the flask. So put a few pieces of the broken porcelain into the flask with a stopper. Then we connect the flask to a Liebig condenser. We connect the flask with a Liebig condenser using the delivery tube. Then we place about 200 centimeter cubic clean empty beaker or control flask as a receiver at the end of the Liebig condenser. We circulate water in the Liebig condenser. We heat the flask strongly on a tripod stand with a wire mesh or wire gauze until there is no more visible boiling bubbles in the flask. Until there is no more visible boiling bubbles in the flask. So what are we observe after having done this? What do we observe? Copper 2 sulfate crystals. Copper 2 sulfate crystals. Copper 2 sulfate crystals dissolve in water to form a blue solution. On heating, colorless liquid is collected in the receiver. Then the blue crystals remain. Blue crystals are left in the flask. Blue crystals are left in the flask. If gentle heated further, the blue crystals turn to white powder. They turn to white powder. So let's explain this and see what are we doing? What have we done? What are we understanding from this experiment? So on heating blue copper 2 sulfate solution, the colorless liquid or solvent evaporates or vaporizes. The liquid vapor or gas passes through the delivery tube to the Liebig condenser. The Liebig condenser has cold water. Inlet near the receiver and cold water outlet. This ensures efficient cooling. If the cold water outlet and inlet is reversed, the water circulation will be less efficient. So now the inlet and the outlet have not to be reversed, but they have to remain the way they are. So the water in the receiver will be warm in the Liebig condenser. The cold water condenses the liquid vapor into liquid. So the condensed liquid collects in the receiver as a distillate. Remember, in infiltration, we said it is collected as filtrate. In distillation, the liquid is collected as a distillate. So the solute of blue copper 2 sulfate crystals is left in the flask as the residue. So they are all called residue. During simple distillation, therefore, the solution is heated to vaporize the solvent, or the one component which is condensed at a different part of the operator. So the purpose of pieces of broken porcelain or porous pot or glass or sand. So this one of this is used inside the flask. the one that we are heating. So porcelain or porous pot or glass or sand is to prevent bumping of the solution during boiling and ensure smooth and even boiling. So salt seawater can be made pure through simple distillation. Remember, salty seawater is not pure but can be made pure through simple distillation. So any mixture with a large difference between 40 degrees Celsius in boiling point can be separated using simple distillation. Then now let's look at the setup of the apparatus. This now is the setup of the apparatus that now we are talking about. Down here you have the source of heat, tripod stand that has a wire gauge on it. Then you have a conical flask with either broken porcelain or sand. Like we said, one is to prevent bumping and also to ensure even distribution of the heat. Then you have a delivery tube from the conical flask to the receiving end. The conical flask is fitted with a stopper. Then we have a Liebig condenser that has an inlet and outlet. So the first one we have as the outlet. Then the second one is the inlet. So the inlet is towards the receiving the end. The inlet is towards the end. The reason as to why the inlet is towards the end, now we are getting in cold water so that it can be able to condense this the vapor back into a liquid. Then the outlet. Then you have the outlet. So that's how the setup of the apparatus is. That's the setup of apparatus is. And now let's look at, so we have two kinds of distillation. You have simple distillation and fractional distillation. So the first one you have looked at is simple distillation. Here you say that salty seawater can be purified through simple distillation. Now let's look at fractional distillation. So fractional distillation is an improved simple distillation. Used specifically to separate miscible mixtures. Remember the other one, it is so for the miscible mixtures, they are now liquids. And for the simple, this was fractional distillation. Then for the simple distillation, remember now it is a soluble mixtures. So fractional distillation is an improved simple distillation used specifically to separate miscible mixtures with very close or near boiling point. So fractional distillation involves heating the mixture in conical or round-bottomed flask or flat-bottomed flask. So the pure substance with a lower boiling point and thus more volatile evaporates or boils or vaporizes fast. So pure ethanol has a boiling point of 78 degrees Celsius. Water has a boiling point of about 100 degrees Celsius at sea level, then at 1 atmosphere pressure. When a miscible mixture of ethanol and water is heated and ethanol vaporizes, or boils, evaporates fast because it is more volatile. So in case of the mixture of water and ethanol, when when we are being separated using fractional distillation, ethanol will now vaporize fast because it is more volatile and has a less boiling point. Now the conical or round bottom flask is connected to a long glass tube called fractionating column. Remember, now in the simple distillation, we do not have a glass tube. We have a glass tube, but we do not have a fractionating column. So the purpose of the fractionating column is to offer areas of condensation for the less volatile pure mixture. The fractionating column is packed with glass beads, broken glass, porcelain, or shelves to increase the surface area of condensation. Now the area of the condensation in this it happens in fractionating column. For the simple, it is the Liebig condenser. So when the vapor rise, they condense. They condense. And the glass beads, or the broken glass, or the porcelain, or the shelves which become hot when the temperature of the glass beads or the broken glass is beyond the boiling point. Is beyond the boiling point of the less volatile pure substance. So the pure substance rise and condensation takes place on the glass beads or porcelain glass or broken glass or porcelain at a higher level on the fractionating column. The less volatile pure substance trickles or drips back into the fractionating column. So fractionating column will tend to bring back the liquid that has not reached its boiling point to be heated again. So if the temperature on the glass beads, broken glass, is beyond 78 degrees, the more volatile pure ethanol rise to condense on the glass beads or the broken glass or porcelain or the shelves higher in the fractionating column. Now it condenses in the fractionating column. Then water condenses and then drips back to the glass or back to the glass beads lower in the fractionating column. Now, for the one that has already reached the condensation or the boiling point, is now dripping, but on the higher end. But now the one that has not, it is dripping on the lower end because it is less volatile. The fractionating column is connected to a Liebig condenser. So remember, condensation now in the simple distillation takes place in the Liebig condenser. But now in this one, we have fractionating column that ensures that the one that has not reached the evaporation, the boiling point, now it remains in the fractionating column, but now in the lower end. The one that has reached it is in the fractionating column, but now on the higher end. Now the Liebig condenser has cold water it has cold water. Now the one that condenses, cold water, inlet and outlet circulation. The more volatile mixture that reaches the top of the fractionating column is condensed by now the Liebig condenser. Now the Liebig condenser is works now just to condense. It has a circulation of cold and hot water in and out, has an outlet and inlet. So it condenses that liquid into a receiver and it is collected as the first fraction. Collected as a fraction. Now in a fractional distillation, we are collecting fraction. In simple distillation, we are now collecting just one. Remember this. We have in fractional distillation, we have fractional distillation. You have on the two liquids, but in simple distillation, you have only one liquid. So at the top of the fractionating column, a thermometer is placed to note or monitor the temperature of the boiling mixtures. The pure substance have constant or fixed boiling points. When one mixture is completely separated, the thermometer reading rises. The thermometer reading remains at the 78 when ethanol is being separated. When no more ethanol is being separated, the mercury or alcohol level in the thermometer rises. Once now the ethanol has already boiled out, now it is time for the water, now it starts rising. The second fractions are collected in the receiver after noting a rise in the mercury level in the thermometer. The thermometer reading rises to 100 when water is being separated. It is passed through the Liebig condenser with the cold water inlet and outlet circulation. It is collected at different receiver as the second subsequent fraction. Second fraction. Now the first fraction now for the ethanol, the second one for water. So each fraction collected should be confirmed from known physical or chemical properties or characteristics. For example, ethanol is a colorless liquid that has a characteristic smell. When it is put in a watch glass, then ignited, it catches fire and burns with a blue flame. So that's how we can test if it is ethanol. That's how we can test ethanol. Then water is a colorless liquid that has no smell or odor. When it is put in a watch glass, then ignited, it does not catch fire. Now this is the setup of the apparatus. Remember now here we have a thermometer, we have a fractionating column connected via connected to the conical flask. Then the fractionating column is the one that is connected to the Liebig condenser. Remember in the first case we just had the flask glass tube is connecting now the glass with the Liebig condenser. So that's the setup for the fractionating column. So fractional distillation. This is now the setup where I use miscible mixtures. You have the thermometer, you have the fractionating column, you have the Liebig condenser. But now the thermometer fractionating column is not in the simple distillation, only found in the fractional distillation. Distillation. So for fractional distillation has a fractional distillation has an industrial application on large scale. Fractional distillation is used in fractional distillation of crude oil in an oil refinery. Crude oil is a mixture of many fractions. When heated, Remember, the first one we are collecting a distillate, but in this fractional distillation we are collecting fractions. So crude oil is a mixture of many fractions. When heated in a furnace, the different fractions separate out according to their boiling point. Now that is in Kenya, fractional distillation takes place at Changamwe in Mombasa. And then fractional distillation of air. Air contains a mixture of three main useful gases which are condensed by cooling to very low temperatures of about -200 degrees Celsius to form a liquid air. The liquid is then heated. Nitrogen is the most volatile at -196 degrees Celsius, and thus comes out the first fraction. Argon at -186 degrees Celsius, then oxygen at -183 degrees Celsius. The three gases are very useful industrial gases. So this now the setup. This is just an example of the setup now of the oil refinery company. So the fractionating column, we have the furnace heat. So each fraction is able to be collected at different boiling point, and depending on the boiling point. We have petrol, we have naphtha, we have kerosene, we have diesel, we have fuel oil, we have lubricating oil. So petrol for driving light motor vehicles. So light motor vehicles, they use the petrol or the gasoline. So naphtha is for making other chemicals. Naphtha is used in making other chemicals. Kerosene for jet fuel and domestic lighting and heating. So kerosene collected for jet fuel and domestic lighting and heating. Diesel for for driving heavy motor vehicles. You have fuel oil for driving factory machines and ships. You have lubricating oil for reducing friction in machines. Then you have bitumen for tarmacking roads. So that's the industrial fractional distillation of crude oil in an